Have you ever stared at a chemical formula, you know, just a string of letters and numbers, and thought, how on earth do we know what that actually looks like? I mean, how do you go from something on a page to a real 3D shape? Well, that's exactly what we're going to break down today. Right. That's the big question, isn't it? It kind of seems like magic, but I promise you it's not. It's actually a brilliant process of deduction, almost like being a detective cracking a code. And in this explainer, we're going to crack that code together, step by step. So, these are our two puzzles for today. Yeah, they look a little intimidating at first glance. On the left, we've got an iron compound, and on the right, one with copper. By the time we're done here, you'll know exactly how to figure out the hidden shapes locked inside these formulas. Now, to solve this, we are definitely not just guessing. There's a system, a clear, repeatable process that lets us turn that formula into a physical shape.
Think of it like a 4-step mission. Each step is going to give us another critical piece of the puzzle. And with each one, the final 3D structure gets clearer and clearer.
Okay, step 1. Our very first clue is all about the central metal atom in each compound. We have to figure out its specific electrical charge, what chemists call its oxidation state. This is the bedrock for everything else we're about to do. Let's dive in with our iron compound. So we know a couple of things right off the bat. Each of those 6 cyanide groups has a -1 charge, and the total charge of the whole thing is -3. So it's just a bit of simple algebra. The charge of the iron plus 6 times -1 has to equal -3. When you solve for iron, you get +3. That's our number. So our iron atom isn't neutral at all. It's an ion with a +3 charge. Lock that number away. It's super important. Now, let's do the same for the copper compound. And honestly, this one's even easier. Ammonia is a neutral molecule, so its charge is just 0. The whole ion has a +2 charge, so the math is super simple. The charge of copper plus 4 times 0 equals +2. Which means, of course, that the copper atom is an ion with a +2 charge. Perfect. Step 1 is done. We've got our charges. Now let's see what that means for the electrons. All right, now that we know the charges, we can figure out the electron blueprint for each metal ion. We need to know exactly how their electrons are arranged because that's what's going to tell us how they can bond with other things. So, a regular, neutral iron atom has its electrons arranged like this. But our iron, the Fe3+ ion, has lost 3 electrons. And here's the key. It always loses them from the outermost shells first. After those 3 are gone, we're left with 5 electrons in a really important inner shell, the 3D orbital. And it's a similar story for copper. A neutral copper atom has its own unique electron setup. To become Rcu2+ ion, it loses 2 electrons, again from the outside in. That leaves it with 9 electrons in that same 3D orbital. Great, we have our 2 blueprints. Okay, this is where things get really cool. Those other molecules attached to the metal, we call them ligands, they don't just hang around passively. Nope, they have a massive influence on the metal's electrons and they can completely change the game. As it turns out, both cyanide and ammonia are what we call strong field ligands. You can think of them as having a really strong personality. When they get close to the metal ion, they exert this powerful electrical field that basically forces the metal's electrons to rearrange themselves. And it is a total game changer. That electron blueprint we just made, well, it's about to get a major renovation. So here's what happens. Remember those 5 electrons hanging out in iron's 3D orbital? The powerful cyanide ligands show up and basically force them to squeeze together and pair up. And look what that does. It leaves some of those 3D orbitals, you can picture them as little rooms for electrons, completely empty. And those empty rooms are exactly what we need for bonding to happen. This just shows that change so clearly. Before the ligands get involved, we have 5 unpaired electrons, each in its own space. Afterwards, they're shoved together, leaving 2 of those 3D orbitals wide open and ready for business. We are on the final step now. We're going to take those empty orbitals we just freed up and see how they mix together or hybridize to form the bonds that ultimately give the molecule its final 3-dimensional shape. Okay, for our iron compound, we need to make 6 bonds for the 6 cyanide ligands. So the iron ion offers up the available empty orbitals, those 2 3D orbitals we just cleared, plus its next available 4s and 3 4p orbitals. We mash them all together, we hybridize them, and we call the result D2sp3 hybridization. Now, the copper compound needs 4 bonds. Its 3D9 configuration is a little tricky, but under the influence of the strong ammonial ligands, something really neat happens. One of the electrons gets bumped up to a higher energy level, which conveniently frees up one 3D orbital. The copper then offers up that now empty 3D orbital, its 4s orbital, and two 4p orbitals. This mix gives us what's called DsP2 hybridization.
And that's it. We've gathered all the clues, we've followed all the steps in our code. Now let's put it all together and see the final picture we've uncovered.
And here it is, the grand finale. It all connects. For our iron complex, that D2sp hybridization we found always results in a beautiful symmetrical octahedral shape. And for the copper complex, the DsP2 hybridization gives us a flat square planar geometry. Look at that, two totally different shapes, and we figured it all out just from their formulas. So we did it. We cracked the code. What started out as just a confusing jumble of symbols is now a predictable, visible 3D structure. And this method, this step-by-step approach, is the key to unlocking the geometry of so many of these complex compounds.
You see, it isn't magic at all. It's just a really satisfying logical puzzle. And now you have the key. So the only question left is, what other molecular mysteries are you going to solve next?